All right, ladies and gentlemen, welcome back to AP Chemistry with Mr. Kenton. Welcome to 2021. Isn't this exciting? We've made it into a new year. I was talking with Mr. Lamberth, and he was talking about how you guys thought, maybe this is just Mr. Lamberth's kids, I don't know, but you felt like I was taking a really long time to say the things that I needed to in my videos. I'm sorry that that's really inconvenient to you, but I'm truly trying to make sure that I give you guys the best instruction possible. Okay, maybe I'm trolling you guys a little bit, but I digress. So welcome back. It's good to be here. So we've already started Unit 5, and so I'm just going to be making some videos here to kind of recap some of the things that we've already done. So maybe I'll actually talk a little bit faster. We'll see. So as you guys recall, we're in the Kinetics unit, and it covers Chapter 14 in your book. Isn't that exciting? It's only going to cover one chapter. That's so cool. All right. So the first thing we need to take a look at as we look at kinetics is we need to get a firm understanding of reaction rates. And I think when we dive into this topic, we need to first understand definition of kinetics. What does kinetics help us to understand and know? So chapter 14 in the textbook corresponds to chemical kinetics, and we can define kinetics as the study of how fast chemical reactions can occur. Right? And so we're essentially looking at processes where we want to measure how quickly do they take place, right? Now, for the most part, in the scope of your chemistry courses prior to this, you're probably used to reactions that occur almost instantaneously. Well, the reality is, ladies and gentlemen, that all reactions don't occur instantaneously. Some of them, they do take some time to occur and to take place. And so kinetics just helps us to get a better grasp of just how quickly a chemical process can take place. So it's looking at that and the mechanisms at which those processes undergo. Okay. Now, as we start to look at kinetics and these things that impact rates of chemical reactions, we need to understand that there are 4 factors that are going to influence how quickly or how slowly our chemical processes are going to take place. The first one is going to simply be reactant concentration. What we're going to find is that if we have an increased starting reactant concentration, then what that's going to do is it's going to cause for the process to occur much more quickly. We'll get into the reasons for that a little bit later, but it has to do with the ability for the particles to collide and possibly form product formation. If there's more reactants that are available to collide and form product, then the process is going to start off much more quickly. If you have less reactant, you're going to have less collisions, less opportunities for it to convert into product. So reactant concentration, important factor number 1. Important factor number 2 is temperature, right? And if you think about it, the definition of temperature is a measure of the average kinetic energy, right? And so when we start to look at this, we find that particles, reactions tend to favor when the particles are moving more. Think about gases, right? When gases are at higher temperatures, there's more opportunity for collisions to take place. And so at higher temperatures, we tend to see that there's an increase in reaction rate. Is this always the case? No, but what we can see here is that temperature does play a role in how it impacts how quickly reactions are going to take place. Third thing is the action of a catalyst, or the role a catalyst can play in a chemical process. Now, hopefully from biology, you guys remember that a catalyst is something that can speed up a reaction without being consumed in that process. Obviously, in biology, you would have learned about enzymes. Well, chemical reactions also have catalysts, and we'll talk about how catalysts function, but really catalysts do one of two things. They either provide a lower energy pathway by decreasing the activation energy needed for a reaction to take place, or what they can do is they can improve or cause molecules to change their orientation so that more effective collisions can happen and product formation can take place. So either way, a catalyst is going to speed up a reaction. And then lastly, it's going to be the physical state of our reactants or something to consider, maybe even surface area, right? And so certainly the amount of exposure that your reactants have with their reacting conditions will certainly impact the reaction rate. And I'm going to give you an example of something that's a physical process, but I think will help drive the point forward, right? So if you're trying to dissolve sugar in, let's say, water or tea or something like that, and you use granular sugar or you use sugar cubes, right? The granular sugar is going to dissolve much more quickly because it's going to have greater exposure to the liquid that you're dissolving it in. Whereas the sugar cube itself, much more compact, much smaller portion of the sugar is going to be exposed to the liquid, and therefore it's going to take longer for it to dissolve. Well, the same principle can be applied to our reactions, right? It's going to be much easier for, let's just say, zinc dust or zinc shavings to react with hydrochloric acid than if we just took a giant chunk of zinc and placed it in hydrochloric acid, right? So those are the four things that are going to influence our rates of reaction that we're going to need to consider and keep in the back of our mind. And as we look at kinetics, our goal is going to be understanding chemical reactions at the molecular level, right? And this is a great segue because in the previous unit, we looked at net ionic equations and we were looking at what's really going on at the particle level. How are things interacting here? Well, with chemical kinetics, we're going to continue to look at things at the molecular level and think about what needs to happen in order for a reaction to take place so that we can go from reactants to products, right? Now that leads us into reaction rate, right? We said 5.1 covers reaction rates. What is a reaction rate? Simply put, it's the speed of a reaction measured by the change in concentration with time. Now that's going to be the most common way that we're going to be measuring reaction rate is change in concentration with respect to time, because it's very simple. It's something that can be applied across all different types of reactions, whether you're dealing with aqueous solutions or gases. That's why you're going to see a lot of things with respect to concentration and time. Obviously, when we talk about reaction rate, this is something that needs to be determined experimentally. We can't simply make up a reaction rate and say, oh, I think the reaction rate is X, just because I think it is, right? You would measure experimental data, you would look at that, you would analyze it, then you would be able to determine from that data, oh, this is the rate at which this reactant is being consumed, or this is the rate at which this product is being produced, okay? Now, something for you guys to consider, we said on the previous slide that concentration is the most common way that we're going to be looking at reaction rates, right? But when we take a look at this particular reaction, all of the things that we've listed kind of below that, we've got volume of gas, pressure of gas, concentration, mass loss by reactants, and pH. Each of those things could also be used to determine the reaction rate, right? And so for the volume of gas and pressure of a gas, what you would be looking at, because you've got the formation of the 2 moles of nitrogen monoxide gas on the product side, what we would anticipate is that over the course of the reaction, there'd be 0 volume of a gas initially, but as the reaction is occurring, the volume and pressure of that gas would be going up. So if you could figure out maybe taking volume or pressure measurements every 5-10 seconds perhaps, you'd be able to put together, oh, well, this is the rate of this particular reaction with respect to volume or pressure. Obviously, we have concentration. We could look at that from the perspective of the nitric acid, or we could look at it from the perspective of the copper 2 nitrate, or even the nitrogen monoxide gas. If we wanted to look at it from the perspective of mass loss by the reactants, then thinking about what's going on with the mass of copper as this process is taking place, right? What was our initial mass when we started this process? What was the final mass of copper in the end? And then lastly, pH. So as the nitric acid is being converted over to the copper 2 nitrate and nitrogen monoxide gas, we're going to have a decrease in the amount of H plus ions that are present in the solution. And so therefore we would anticipate to see an increase in the pH as the course of this reaction was going on. So looking at those things, those are just a couple of other ways that we could measure a reaction rate that is not necessarily concentration specifically. Now again, we're going to be using concentration the most, but I just want you to keep that in the back of your mind that it's not limited to just concentration. I hope that makes sense. All right, let's talk more about reaction rates then. So let's imagine that we have an imaginary reaction where we've got reactant A is being converted to product B. And so from our perspective, there are really two ways that we could measure the rate of this particular reaction, right? We could look at it from the perspective of what's going on, what's changing with respect to A, so the speed at which the reactants are disappearing, right? And then we've also got it from the perspective of the rate of appearance, or the speed at which the products B are appearing during this particular process, right? Now, obviously, when we think about this, the rate of disappearance, we would say it'd be a negative value. The rate of appearance would have a positive value. Now, as we begin to look at reactions, some reactions are reversible. Our reactions that have double arrows or that are at equilibrium are reversible. And so what we need to consider in those reactions is that as products accumulate, there's a possibility that they can begin to turn back into reactants, right? And so, in fact, what we know is that when the reaction rates of the forward and reverse processes are the same, so when the rate of the forward and the reverse process are the same, that's when we know that we're at equilibrium. That'll come in handy later. We'll revisit equilibrium in Unit 6. Okay, now as we look at reaction rates, it's important to recognize that early on in the process, because you're starting, let's say, with reactant A, we have no B, then it's only going to be dependent on the amount of reactants present. Okay, and so it's going to be imperative to us, as we're looking forward, and even for chemists, that when they're measuring reaction rate, they want to be able to get a measure of the reactants as soon as they are mixed together. Now, obviously, in this particular process, we've only got one reactant going to one product, so it's a little bit more difficult there. But when you have multiple reactants, it's going to be extremely important that we get a pulse or a measurement of the reactant information as soon as we mix the vessel, right? Now, again, I've mentioned it already, but the most useful and general way of measuring the rate of a reaction is going to be in terms of change in concentration per unit time, right? And so we think about it, the rate of a reaction is going to be equal to the change in concentration of A with respect to the change in time, or divided by the change in time. We could also write it with respect to B. We could say the rate is equal to the change in concentration of B divided by the change in time. Now again, our most common units for rates are going to be in molarity per second. And if you're not remembering, or if you're having a moment where you're not remembering what molarity is, remember molarity is simply moles over liters. So moles of our substance divided by the liters, or the volume of the solution, okay, or volume of your container. All right. Now, here's another way that we can approach looking at reaction rates. So we had that perspective of thinking of it as the change in the concentration divided by the change in time. Well, we can also look at reaction rates from the perspective of the stoichiometry of a balanced equation. So here we've been given the reaction of 2 moles of dinitrogen pentoxide is producing 4 moles of nitrogen dioxide and 1 mole of oxygen gas. Okay, so we've got that balanced equation, and when we look at this, hopefully this makes sense to you guys, is that for every 1 mole of oxygen that appears, because it has a coefficient of 1, that means that 4 times as many moles of NO2 will appear during that same time period. That makes sense? Now, likewise, in the meantime, twice as many moles of N2O5 will be disappearing as moles of O2 are forming. Again, that's with respect to the stoichiometry of that particular process, right? So what we would anticipate then is that the rate of disappearance of N2O5 would be twice as much as that of O2. Or the rate of appearance of NO2 would be 4 times as fast the rate of appearance of O2. That makes sense? Right? So if we start to think of it from the stoichiometry perspective, we could then start representing rates as a function of their stoichiometry. And so what we've seen is that when we have changes in concentrations of reactants and or products, it's going to be inversely proportional to their stoichiometric proportions, right? So the big thing you need to take away from this is that when we're dealing with concentration and we've got stoichiometry and we're looking at rate, the stoichiometry and the change in concentration or the rate is going to be inversely proportional, okay? Hopefully that makes sense. And so if we're looking at this particular reaction, we could write the reaction rate the following way, right? We could have the rate with respect to each substance here. So the rate with respect to the reactant and the two products. So you'd have a rate that's negative 1/2 the change in concentration of N2O5 divided by the change in time. Or you could say the rate is equal to 1/4 times the change in concentration of NO2 divided by change in time. Or you could say the rate with respect to oxygen is going to be the change in concentration of oxygen divided by the change in time. Okay. Now, those rates, because it's the same process, they're going to be equal to each other, right? Now, one minor thing here to keep in mind, notice that we put a negative sign beside that N2O5. That's just going to remind us that the N2O5 is disappearing as this process is taking place. And so, obviously, we have this set up for a very specific example. You can use this same relationship, kind of what we've written here for that specific reaction. If we have a more general reaction, we can come up with a similar way of expressing the rate for the reaction. So let's say we've got general equation where it's got coefficients of A, B, C, and D in front of substances A, B, C, and D, right? And so the rate would be represented in the following manner. It would essentially be set up as -1 over the coefficient of any of those substances times the change of that substance divided by the change in time, right? So I think you guys can read that. I'm not going to go through and read off kind of those rates, but hopefully that makes sense to you guys. All right, we got 2 more slides, I think. All right, so here's a specific example that Mr. Lamberth and I put in here. Really, Mr. Lamberth, he made these slides, at least specifically these ones, but that's neither here nor there. So when we look at reaction rate, one thing we want to notice is how the products increase to concentrations that are proportional to their mole ratio. And again, for this process, something to note is that we're assuming that it's going to completion. There's not an equilibrium process that's taking place. And so what we can see, we know that rate is going to be equal to, from a data perspective, change in concentration should be final minus initial amount over finite minus initial time. And so if you're looking at the graph over there, we look at the graph and we've seen the blue curve, we got an initial concentration of N2O5 of 0.16. Now, notice at the beginning, because we haven't had a change in time, we have no rates, no reaction rate, because the reaction hasn't started yet. Now, after time equals 2 seconds, we can go and take a look at the graph. And so if we're following the graph here at time equals 2 seconds, it looks like we've got about 0.08 molar concentration of N2O5. Well, that being the case, we can then start to set up and calculate for our rate at that particular point, right? So we do final minus initial. So it should be 0.08 minus 0.16, right? And that's going to give us negative 0.08. divided by 2 seconds, so we get a rate that's negative 0.04 molar per second. Likewise, if we start looking at the other substances, NO2, that's our red curve, time equals 0, there was none of it, but at time equals 2 seconds, we're at about 0.16 molar. So we do 0.16 divided by 2, gets us a rate of NO2 that's 0.08 molar per second is how the rate of its appearance. And then for oxygen, that's our green curve, going from 0 to 2 seconds, we get about 0.04 molar. So 0.04 divided by 2 gives us 0.02 molar per second. And then we get a reaction rate, which is calculated by taking the rate of our substance and dividing it by its coefficient in the stoichiometry. And hopefully what you would notice is that for all of those, if you follow that process, 0.04 divided by 2, that gives you 0.02. 0.08 divided by 4, that gives you 0.02. 0.02 divided by 1, that gives you 0.02. Okay? And so I'm not going to take the time to walk you through all of these steps, but you can see how the calculations are done. One last thing to note, notice that as the concentration of N2O5 decreases, we see that the reaction rate is also decreasing. Okay, that should match up with what we stated earlier of how reactant concentration has an impact on rate. When there's a higher concentration, the rate's faster. When the concentration's lower, like what we have at time equals 8 seconds, the rate is significantly slower. It's slower by a factor of 10. Okay, I hope that makes sense. All right, last slide, and then I'll be done with this particular video. All right, so here's another example of a reaction. We've got chlorobutane reacting with water to make butanol and hydrochloric acid. Now, if we have data, we can plot the change in the concentration versus time, right? And so the textbook does this. They have data that they pull and they created this curve, right? So we've got our data points at our various times at 0 through 900 seconds. And one thing that it's important to recognize here is that the average rate of the reaction is going to decrease over time. All right, that should make sense, right? Starts off initially, maybe it's going a little faster, but then as we get to lower and lower concentrations, notice that we start having less and less change in our chlorobutane, right? So average rate of reaction is going to decrease with respect to time. The other thing that we need to consider is that the rate at any instant in time is the instantaneous rate. And so this is going to be the slope of the tangent, the line that's tangent to the curve at that particular point. Now, real quick note, I know in my class we took some time to talk about this. You're not going to be asked to find lines that are tangent to curves and determine instantaneous rates using graphical data like this, okay? We took the time to talk about it in class, but there's not going to be anything like that on the AP exam because everything that we're looking at here, at least from AP's perspective, should be able to be done without the use of calculus, okay? Now, one last thing to mention, we should be able to recognize that the instantaneous rate is different from the average rate, okay? And so when we refer to the rate of a reaction, it's going to be our assumption that we're going to be dealing with the instantaneous rate unless we're told otherwise, right? So, like they have here, finding the instantaneous rate at time equals 0, that would be the initial rate of reaction, right? So if you're asked about rate, they're probably asking you to find the instantaneous rate of that particular reaction, okay? One last mention on instantaneous versus average, if maybe you're still a little confused with that. Think about it from the perspective of like you're taking a car trip, right? And let's say you travel 400 miles and it takes you 5 hours to do it, okay? And so that means that you are traveling at an average speed of 80 miles per hour. Now, the reality could be is that maybe at time equals 2 hours, you were taking a stop and you were getting off on an exit ramp. Well, when you were on the exit ramp, let's say that was at time 2 hours, you were going at a speed of 35 miles per hour. Your instantaneous rate in that particular moment is not going to be 80 miles per hour, it's 35, right? So just keep in mind, instantaneous is different from the average rate. And hopefully that example of speed, like at one given time during your trip versus the overall trip, kind of helps make sense of that. All right. So that's all I've got for you, ladies and gentlemen, for this particular video. I'm going to be putting out something next here pretty soon that has me working through some of these problems before we get into topic 5.2. Thank you so much for watching this. Hope it was helpful. Let us know if you have any questions, and I'll see you guys again soon. Take care.